right, in this video we're going to be looking at the basics of graph theory. I think you'll be watching this around April 15th. So graphs are not probably what you used to think graphs were, at least in this setting. So typically when you're studying like one variable functions in calculus or something, you talk about the graph of the function, which is a plot of the points of the graph in 2 dimensions, let's say. When we're talking about graphs in graph theory, we're talking about diagrams that have points and lines. So I'm going to go through like the basic vocabulary and look at a bunch of examples, and then we'll start proving some theorems about these graphs throughout chapter 10. So graphs, these diagrams of points and lines, are really useful structures for modeling certain objects in mathematics and science. So anytime you have, you're studying like a collection of objects or items that any two of which may have a relationship, and that might be like a physical connection, like in a network, nodes of a network might be physically connected somehow, or it could even be like an abstract connection, like a relationship like friendship or, some genetic relationship or something. So anytime you have something like that, a graph may be used to model that relationship system. Okay, so let me just kind of start making some drawings and telling you the types of objects that we're going to be studying. So a graph is a diagram. And formally, it's a collection of sets, but it's a diagram that we think of as a drawing that consists of some points, which we call vertices, and an individual one would be called a vertex, singular is vertex, and then some lines, which may or may not connect some of these points, all right? So this is an edge. Yeah, the lines are called edges, and the edges must connect to vertices. You can't have like a dangling edge that doesn't have a vertex at either end, like that. Okay, and we can actually have edges that connect a vertex to itself. So these are the edges. And taken together, the vertices and the edges form what are called a graph. Okay, and so formally, what a graph is a set of vertices, say V1, 2, 3, 4, and 5, like in this picture, and then a set of edges, E1, 2, and E3, and then a description of the relationship between the edges and the vertices. Each edge should be connecting a pair of vertices. So we think of that as like a function, an edge endpoint function. So in this case, the function would report what the endpoints of E1 were. So I'm going to go over here to this diagram and like make it match the thing that I'm building. All right, and let's make this one edge 1, edge 2, and edge 3. Okay, so the relationship I described using the function is that edge 1 connects vertex 1 to vertex 2. And then edge 2 connects 1 to 3. And finally, edge 3 connects vertex 3 to itself. So this is a formal way of describing the diagram that I have here. So let me go through the rest of the vocabulary I see in these boxes that I took from the book. We call the vertices at either end of an edge the endpoints of that edge, similar to the usage of endpoints of an interval on the real line or something. An edge that connects a vertex to itself, like this one, is called a loop. And if you happen to, in your diagram, have a couple of edges that connect the same pair of vertices, so in general that's sort of allowed. So for example, let's say I consider a graph that looks like this. These two edges are called parallel edges. Okay, and now I want to introduce the notion of adjacency. Two vertices are called adjacent if there is an edge connecting them. So V1 is adjacent to V2 in this graph, and V2 is not adjacent to V3 because there's no edge connecting them. Vertex is called adjacent to itself if there's a loop at that vertex. So V3 is adjacent to itself, like this. And then we have a word to describe when a vertex is connected to an edge. That's called incidence. So we would say here that this edge E2 is incident on V3 because it hits V3, and it's also incident on V1. Okay, and then the last notion that I have here in the first box is isolated. An isolated vertex is a vertex that has no edges incident on it, right? So V4 and V5 are isolated vertices in this graph G. Okay, and towards the end of this section, they talk about the degree of a vertex, and I thought I would just kind of move that up front a little bit because it's a pretty important concept. So if you look at any vertex in a graph, you can count the number of edges that are incident at that vertex. So for example, at an isolated vertex like V4 or V5 in this graph, there are no edges connected. In that case, we call the degree of, for example, vertex 4, 0. That means there are no edges attached to it. The degree in this graph of vertex 1 is 2, right? And the degree of vertex 2 is 1. And as you can see here in the definition, an edge that is a loop is counted twice. So the degree of vertex 3 is 1, 2, 3. And you can see it visually. There are 3 lines coming out of vertex 3. So let me try and squeeze this in here. And actually, just to finish off all of the degrees in this graph, the degree of vertex 5 is also 0. So now I've described the degrees of all of the vertices in the graph G. And I want you to note, the total degree of the graph then is just the sum of all of these degrees. So we could also attach a measurement to the graph G from the degrees of all these vertices. So in this case, the degree of the graph is 3 plus 2 plus 1 is 6. Okay, and down here, just for practice, the degree of this vertex is 2, the degree of this vertex is 3, and the degree of this vertex is 1. So I want to emphasize that what the graphs are modeling is not entirely something geometric, although that's how we usually study the graphs, is by drawing them. What they're just modeling is an abstract relationship between the vertices, whatever those are representing, and the edges, which are the connections. So to emphasize that, I want to point out that every single graph has like infinitely many ways that you can draw it, and the drawing a graph differently doesn't mean you're changing the graph. So let me start with a graph G described by the following vertex and edge set. Okay, so I've described 5 vertices, 5 edges, and as concisely as I could, I described the connections between them. So how this is read is that the edge E sub I connects VI to VI plus 1. And then that is true for all i's in between 1 and 4. And edge 5 connects vertex 1 to vertex 5. So let me come up with more than one drawing of this one graph. Here's one drawing of that graph, and let me go ahead and number the edges so that you can verify that I have set it up properly according to this description. But also I could draw it like this. It doesn't matter how I arrange the vertices, or even if I make the edges like straight or anything. I mean, I can just, as long as the connections are satisfied, then it's a valid drawing of the graph. Okay, so you can see that this drawing looks completely different than this drawing, but it is exactly the same graph that this drawing is describing. And let me also point something out while we're looking at this type of graph. We understand that when, you can totally draw graphs and have the edges cross each other, that's no problem. But this crossing is sort of artificial. There's no vertex there, so it doesn't describe any sort of relationship between points and lines connecting them. So the crossing there is not a geometric feature of the graph. So for example, this little line segment is not considered an edge in the graph. It's this full line segment like this. All of these crossings are just sort of artificial, if that makes sense. Okay, another definition. Sometimes we are concerned with not only relationships between pairs of objects in our model, but sometimes we are interested in sort of one-directional relationships instead. So for example, like if you were looking at a family of people or something, you could take any two people and consider the relationship one person is older than the other person. Well, that's not really a two-way relation, right? Or a symmetric relation, if you will. So when you are maybe drawing edges to describe that relationship, you can make them directed with little arrows, and that will indicate some sort of, one-directional edge rather than a bidirectional edge. So any graph that has arrows instead of edges is called a digraph or directed graph. And each of the edges is considered a directed edge. So you might recognize directed graphs from when we were studying relations, right? And I think most of the graphs that we're going to study in this chapter are not directed graphs, but you can imagine, anytime you're like studying a relation that is sort of one directional like this, a diagram could be helpful, right? So you want to you want to be able to have these at hand. Okay, so one more definition, then we'll start looking at some specific problems. A simple graph. These are the types of graphs that we're mostly going to be studying. So a simple graph is a graph that does not have any loops and does not have any parallel edges. And we're going to be studying like regular graphs, not digraphs. So we're just going to be studying graphs that kind of look like this. This is a perfectly good simple graph. Okay, so a really good practice is to study drawings of graphs that are, just appear in the chapter or elsewhere, and study them, like study the vocabulary that we've talked about so far, in particular degrees of vertices and total degree of the graph. And then it's also important to practice building your own graphs. And in this set of exercises from the section, I've assigned some of the even ones for you to do for homework, but they help you just get used to how vertex degrees appear in graphs, and it's asking you to decide, sort of what is a possible set of vertex degrees and what are some impossible sets of vertex degrees. So let's do some of the odd numbered problems. Let's see if we can draw a graph that satisfies these degrees or prove that it couldn't possibly happen. Okay, so in number 17, we're supposed to try and build a graph on 5 vertices. And these right here are supposed to be the numbers of edges incident in each of these vertices. So each of these is the vertex of a specific degree in this graph, a vertex in this graph. So, okay, let's try and construct such a thing. One vertex has to have degree 1, so it's going to be connected to some other vertex, right? Another vertex is supposed to have exactly 2 incident, so how about this one? All right, I'm doing well so far. Another one is supposed to have degree 3, so let's make this one degree 3, but be careful, I can't connect this back to that one, and I don't want to connect it back to this one because I don't want to increase the degrees of these two vertices because I've sort of like settled on what their degree should be. So for this one, I can connect to there and to there. And, at the moment, I'm feeling good about my construction because 3 of the vertices have, the specified degrees. But then I get into some trouble, right? Because I want to have these last 2 vertices have degree 3 and degree 5. But hold on a second. If this, for example, is to have degree 5, it's going to need to be connected to 5 other vertices. Hold on, I gotta stop and think about this. So now I'm going to try and add some more edges and complete the degree requirements that they've given me. So I really want this vertex to have degree 3 and this one to have degree 5, but I don't really want to go around adding edges to any of the 3 vertices that I've already settled on, right? So what I can do is I could add loops, right? Like this, the degree of this vertex is already 1. If I add a loop, then it has degree 3. And over here, if I add 2 loops, then I have a degree 5 vertex. Okay, so I just kind of played around with it and I was able to get a graph for number 17. Let's see if we can do number 19. So let me try. I want 3 vertices of degree 1. So how could I do that? Well, if I add an edge like this, then each of those vertices has degree 1. I wouldn't be able to use a loop to do this because if I put a loop on a vertex, it gives it degree 2. So that's no good. So if I want 3 vertices of degree 1, then I'll probably have to do something like this. And then one of those vertices needs to be chosen to try and be degree 4. And so I think, okay, how am I going to do that? I got to increase the degree on this thing. Best thing I can do is add a loop because I don't want to increase any of these degrees. But I'm sort of stuck at 3 because if I add another loop, then I'm up to 5. And in fact, I'm only going to be able to make this, the degree of this vertex odd. So this is no good, right? And we start to realize, there's not much else I can do to try and get these degrees, this degree sequence. And I realized pretty quickly that, something's wrong here. It can't be done, and I want to articulate why. So let's think about it this way. When I am counting the degrees of each vertex, I am counting each edge a couple times, right? So like, look at the 2 edges in this graph. If I go around identifying the degrees of the vertices that these edges connect, then I visit each edge exactly twice, right? So this edge connects these 2 vertices, so it contributes 1 to the degree of this vertex, and it also contributes 1 to the degree of this vertex, right? And it's the same, like, come up here. Every single edge in this graph, I've got like 1, 2, 3, 4, 5, 6, 7 edges. Each of those edges, whether they're normal edges or loops, contributes 1 to the degree at one end and 1 to the degree at the other end. So this edge contributes 1 to this degree, it contributes 1 to this degree. This edge contributes 1 to this degree and this. And then like this loop, for example, contributes 2 to this degree. So every single edge, let me say it like this, every edge contributes 2 to the degree count. And by degree count, I mean the total degree of the graph. So you have however many edges you have in the graph, and each contributes the number 2 to the total degree. So what does that mean about the total degree of a graph if every edge is contributing the number 2 to its count? Well, that would mean that the degree, a total degree of a graph has to be an even number, right? And this is an issue when it comes to trying to arrange the degrees of the vertices being 1, 1, 1, and 4, because this would mean that the degree of such a graph would have to be 7, which is odd. And apparently that can't happen. So let's sort of put that under our definition of degree as a theorem. And in fact, I can come up with a formula for the total degree in terms of the number of edges, right? By our observation, since every single edge in the edge set of the graph contributes 2 to the total degree, this is our formula. So I could kind of write it symbolically like this. The degree of a graph G is equal to 2 times the number of edges, or the cardinality of the edge set. So that's a handy theorem, especially for disproving the existence of a graph of a certain degree set. Okay, so as I move on to a couple more examples, however many I can fit here, let's keep that in mind. So can I come up with now not just a regular old graph, but a simple graph? Remember, simple graphs don't have parallel edges, nor do they have loops. Can I come up with a simple graph with 4 vertices of these degrees? Well, first let me check to see if the total degree is even. Yeah, I think this is degree 10. I should be able to arrange that and not violate that theorem, but let's see if there's anything else about the requirements that rule this possibility out. So okay, I'm just going to try and build this thing. Degree 1 means I'm only allowed to have 1 edge coming out of there. And then degree 2 might look like this, right? And then I need a 3, and then I need a 4. So this vertex is going to have to be, incident at 3 edges, and I'm not allowed to draw a loop, right? So the best that I could do here to increase this vertex's degree is to add an edge like this. I don't want to add an edge back to these previous 2 vertices because I don't want to increase their degree. So I have a feeling that this cannot be done. And here, let's just write a small explanation for why it cannot be done. Probably the easiest way to argue this is to rule out the possibility that there's a degree 4 vertex in a simple graph of 4 vertices. So I'll try and explain that. Okay, so I'm happy with this type of explanation. I'm going to make the claim that no simple graph on 4 vertices can have a vertex of degree 4 because there are only 3 other vertices in the graph that you're allowed to connect that vertex to. You can't connect the vertex to itself because we're talking about a simple graph. There can't be any loop at any given vertex. So since there are only 3 other vertices that a given vertex could be adjacent to, that puts the maximum degree of any vertex in a simple graph on 4 vertices at 3.